Hello there, and welcome back to Sleep Science Time. It's genuinely lovely to have you here again. Thank you for tuning in tonight, and for choosing this moment to let everything else fade away. Tonight, we're going to explore a theory so mathematically beautiful, so philosophically peculiar, that it's either the greatest achievement in theoretical physics or the most elaborate intellectual wild goose chase in scientific history. We're talking about string theory. Now here's the thing about string theory. It suggests that everything in the universe, you, me, the stars, the atoms in your pillow, isn't made of particles at all. Instead, at the smallest possible scale, everything is made of tiny, vibrating strings of energy. Different vibrations create different particles. The universe is essentially a cosmic symphony, and we're all just different notes being played. It's absolutely bonkers when you first hear it, and yet the mathematics works so elegantly that thousands of physicists have devoted their careers to it. We'll start from the very beginning, from the problem that made physicists desperate enough to propose invisible strings in the first place. Then we'll journey through the wild developments of the 1980s, when string theory exploded into multiple dimensions we can't see, through the controversies and the brilliant minds who either championed or criticized it, right up to where we are today, still unsure if it's correct but unable to let it go. And then, near the end, we'll venture into the truly fascinating bit. What string theory might mean for time travel, for parallel universes, for the very nature of reality itself. Fair warning though, by the end of this you'll either be peacefully asleep or lying there wondering if you're actually a one-dimensional string vibrating in 11 dimensions. Both outcomes are perfectly acceptable. Before we dive in, I'm curious about something. Think about the last time you felt absolutely certain about something, only to discover you were completely wrong. Maybe you were convinced your keys were in your jacket, but they were in your bag. Maybe you believed a fact for years before learning it wasn't true. That feeling of certainty dissolving into uncertainty, that's rather what string theory does to physics. String theorists are brilliant people who desperately want to be certain they're right, but the universe refuses to give them a clear answer. Have you ever felt like that about something important? That strange space between knowing and not knowing? Drop a comment and let me know. And if you enjoy these gentle explorations into the strange corners of science, a like and a subscription would mean the world to me. It genuinely helps this little channel reach other people who enjoy drifting off while someone explains why the universe might have 11 dimensions. For those of you returning, thank you. You've become a small community of wonderfully curious, delightfully drowsy minds, and I'm grateful you keep coming back. Now, the usual disclaimer. Falling asleep is absolutely encouraged here. That's the entire point. But if you make it to the end still awake, I hope you'll drift off with your mind softly full of vibrating strings, extra dimensions tucked away where we can't see them, and the peculiar realization that the greatest minds in physics have been arguing about this for 40 years without a definitive answer. Sometimes the questions are more interesting than the answers anyway. Right then, shall we begin our journey into the wonderfully weird world of string theory? So, to understand why anyone thought invisible vibrating strings were a sensible explanation for reality, we need to talk about a rather significant problem in physics. Actually, calling it a problem is putting it mildly. It's more like an existential crisis that's been quietly tormenting physicists since the 1920s. Here's the situation. Physics has two monumentally successful theories. On one side, you've got Einstein's general relativity, which explains gravity and the behavior of massive objects, planets, stars, galaxies, black holes. It's breathtakingly elegant. Gravity isn't a force pulling objects together, it's the curvature of space-time itself. Massive objects bend space around them, and other objects follow those curves. It's geometric, beautiful, and it works brilliantly. On the other side, you've got quantum mechanics, which explains the behavior of tiny things, atoms, electrons, photons, all the subatomic particles. It's also phenomenally successful. We've built computers, lasers, nuclear reactors, and MRI machines based on quantum mechanics. The predictions are accurate to absurd decimal places. It works. But here's the trouble. These two theories fundamentally disagree about how the universe operates. They're both correct within their domains, but they're philosophically incompatible. General relativity is smooth, continuous, deterministic. Quantum mechanics is jumpy, probabilistic, fundamentally uncertain. And when you try to apply both theories to the same situation, say, what happens inside a black hole, or what occurred at the Big Bang, the mathematics explodes into nonsense. You get infinities everywhere. The equations literally break down. Physicists call this the problem of quantum gravity. How do you describe gravity using the rules of quantum mechanics? How do you unite these two pillars of physics into one coherent framework? Now you might think, well, maybe gravity just doesn't follow quantum rules. Maybe it's different. But that seems unlikely. Everything else in the universe is quantum at small scales. Why would gravity be the exception? And there are situations like the earliest moments of the universe or the centers of black holes where quantum effects and gravity are both strong. We need a theory that handles both. People tried for decades to create a quantum theory of gravity using the standard approaches. They'd take Einstein's equations and try to quantize them, applying the same methods that worked for electromagnetism and the other forces. And every time the mathematics produced infinities that couldn't be removed. The theory simply didn't work. By the 1970s, physicists were getting rather desperate. This wasn't some minor technical problem. This was a fundamental limitation in our understanding of reality. We had two brilliant theories that couldn't talk to each other and no clear path forward. Then, almost by accident, someone noticed something peculiar about a theory that had been developed for an entirely different purpose. A theory that, bizarrely enough, involved tiny vibrating strings. And that's where our story really begins. But before we get there, let me ask you something. Have you ever had two parts of your life that just wouldn't fit together? Maybe a hobby that clashed with your work schedule, or two friends who couldn't stand each other and you were stuck in the middle trying to make it work? That's what physicists felt like. They had these two magnificent theories, both clearly correct, and they simply refused to cooperate. Frustrating, isn't it? Right, so here's where things get delightfully odd. String theory wasn't actually invented to solve the quantum gravity problem. It was invented to explain something completely different, and it failed at that. But then, in a spectacular bit of scientific serendipity, people realized it accidentally solved the problem nobody thought it could solve. Science is wonderfully messy sometimes. Let's go back to 1968. A young physicist named Gabriele Veneziano was trying to understand the strong nuclear force, the force that holds quarks together inside protons and neutrons. He was looking through mathematical functions, searching for one that matched experimental data about how particles interacted. and he found one, a function called the Euler beta function, discovered by the mathematician Leonhard Euler in the 1700s. When Veneziano applied it to particle physics, it worked beautifully. It described the interactions he was studying with remarkable accuracy. But nobody knew why it worked. It was just a mathematical coincidence as far as anyone could tell. Then, in 1970, 3 physicists, Yoichiro Nambu, Holger Nielsen and Leonard Susskind, independently realized what Veneziano's formula was actually describing. It wasn't describing point particles colliding. It was describing tiny, one-dimensional strings vibrating and interacting. The mathematics naturally arose from imagining particles as strings rather than points. Now, these strings were incomprehensibly small. We're talking about 10 to the power of minus 35 meters. That's a decimal point followed by 34 zeros and then a 1. To give you perspective, an atom is to a human what a human is to the solar system. And these strings are vastly, vastly smaller than atoms. At any scale we can currently measure, they'd look exactly like points. We'd have no way to detect their string-like nature directly. These strings could be open like a strand of hair or closed, forming loops. They could vibrate in different patterns like a guitar string producing different notes. And here's the clever bit. Each vibration pattern corresponded to a different particle. An electron wasn't a point, it was a string vibrating one way. A quark was a string vibrating another way. The universe was quite literally playing different tunes. It was a beautiful idea. Unfortunately, it didn't actually work for the strong nuclear force. As physicists developed quantum chromodynamics in the 1970s, the correct theory of the strong force, string theory became obsolete for its original purpose. By the mid-1970s, most physicists had moved on. String theory was a lovely idea that didn't describe reality. Case closed. Except, well, not quite. Because a few stubborn physicists kept working on it, and they noticed something extraordinary. When you analyze the vibrations a closed string can make, you find different modes corresponding to different particles. Most of these matched known particles reasonably well, but there was one vibration that didn't match anything physicists had seen. It corresponded to a massless particle with a specific quantum property called spin 2. And there's only one particle in the universe with those exact properties, the graviton. The hypothetical particle that, in quantum mechanics, would carry the gravitational force, just like photons carry electromagnetism. String theory accidentally predicted gravity. It required gravity to exist. This theory that nobody had asked to solve quantum gravity had gravity built into its foundations. You couldn't have string theory without it. This was monumental. Remember, the whole problem with quantum gravity was that whenever physicists tried to create a quantum theory of gravity, they got infinities and mathematical breakdowns. But string theory, by treating particles as extended strings rather than points, naturally smoothed out those infinities. The mathematics worked. It was finite, consistent, and it included gravity automatically. By 1974, physicists John Schwartz and Joel Shirk realized what they had. This wasn't a failed theory of the strong force. This was potentially a theory of everything, a framework that could describe all forces and particles in one unified picture, including gravity. Of course, nobody believed them at first. String theory had already been dismissed. The physics community had moved on. Schwartz and Shirk spent years working in relative obscurity, convinced they'd found something profound but unable to convince others. It must have been rather lonely, honestly. Imagine knowing you've discovered something potentially revolutionary, but everyone thinks you're wasting your time on a dead theory. They kept at it though, refining the mathematics, working through the implications, waiting for someone else to notice. And in the early 1980s, people finally did notice. What followed was one of the most explosive periods in theoretical physics history, a revolution that would sweep up hundreds of physicists and forever change how we think about the universe. But we're getting ahead of ourselves. First, we need to talk about something string theory demanded, something that seemed absolutely absurd when people first encountered it, and still seems absurd today: extra dimensions. Have you ever felt like you were onto something important but nobody else could see it? Like you'd grasped some truth that was obvious to you but invisible to everyone around you? That's what Schwartz and Shirk must have felt in the 1970s, toiling away on strings while the rest of physics ignored them. Sometimes being ahead of your time is indistinguishable from being wrong. The trick is figuring out which one you are. Rest easy with thoughts of tiny strings vibrating in the void, accidentally explaining gravity. Right, let's talk about dimensions. You're familiar with 3 spatial dimensions: length, width, height. You can move forward, backward, left, right, up, down. Add time as the 4th dimension, and you've got the 4-dimensional spacetime that Einstein described. That's reality as far as everyday experience suggests. But string theory has other ideas. The mathematics of string theory only works consistently in 10 dimensions, not 4. 10. 6 extra dimensions beyond the ones we experience. When physicists first realized this in the 1970s, their reaction was essentially, well, that's obviously wrong then, isn't it? If there were 6 extra dimensions, we'd notice. We'd see objects moving in directions we can't point to. The universe would look completely different. But then Oscar Klein and Theodor Kaluza, actually this idea goes back even earlier to the 1920s, had suggested a possibility. What if extra dimensions exist but they're curled up so small we can't perceive them? Imagine a garden hose viewed from a distance. It looks one-dimensional, just a line. But zoom in close enough, and you'd see it has a second dimension curled around its length. An ant walking on the hose can move forward along its length, or around its circumference. String theorists proposed something similar. 6 extra dimensions exist, but they're compactified, curled up into shapes so tiny that at human scales, or even atomic scales, they're invisible. Only at the string scale, that 10 to the minus 35 meters we mentioned, would you notice them. Now you might wonder why the dimensions curled up that way. Why not have all 10 dimensions extended? The honest answer is, we don't know. It's just a feature of the mathematics. The equations allow for different configurations, and our universe apparently chose this one, with 3 large spatial dimensions and 6 tiny compactified ones. Or at least that's what string theory suggests. We have no experimental evidence for this whatsoever, but we'll get to that problem later. Anyway, armed with this 10-dimensional framework, physicists in the early 1980s started working out string theory's implications more carefully. And in 1984, something remarkable happened. Michael Green and John Schwartz proved that string theory was free from certain mathematical inconsistencies that plagued other attempts at quantum gravity. They showed that the theory was anomaly-free, a technical term meaning the mathematics didn't contradict itself. This announcement triggered what's been called the first superstring revolution. Suddenly everyone wanted to work on strings. By some estimates, hundreds of physicists who'd been studying other areas dropped what they were doing and switched to string theory. It was the hottest topic in theoretical physics, a potential theory of everything that unified all forces and explained all particles. Universities rushed to hire string theorists. Conferences were packed. Papers poured out at an astonishing rate. It was an incredibly exciting time, full of optimism that physics was on the verge of its ultimate theory, the final framework that would explain everything from quarks to galaxies. String theory also incorporated something called supersymmetry. This is the super in superstring theory. Supersymmetry proposes that every particle has a partner particle. Electrons have selectrons. Quarks have squarks. Photons have photinos. These names are delightfully silly, and yes, physicists actually use them with straight faces. None of these supersymmetric partner particles have been observed, which is a bit awkward. If they exist, they're much heavier than ordinary particles, requiring enormous energies to create, energies we haven't yet achieved in particle accelerators. Or they might not exist at all, which would be a significant problem for string theory. But in the 1980s, people were optimistic they'd be discovered any day. Now here's where things get complicated. As physicists explored string theory more deeply, they discovered it wasn't just one theory. It was 5 different theories. 5 distinct versions of string theory, each mathematically consistent, each describing 10-dimensional universes with vibrating strings, but each with different details about how strings behaved and what particles they produced. These were called Type 1, Type 2a, Type 2b, and 2 versions of heterotic string theory. Don't worry about the details. The point is, instead of one theory of everything, physicists had 5 competing theories. Which one described our universe? Nobody knew. It was rather embarrassing, like discovering 5 different instruction manuals for reality and not knowing which one to follow. Then, in the mid-1990s, a physicist named Edward Witten proposed something audacious. What if these 5 theories weren't actually different? What if they were just different perspectives on a single underlying theory? Like how a building looks different from different angles but is still one building. This hypothetical unified theory was called M-theory. The M might stand for membrane, matrix, master or mystery, depending on who you ask. Witten never specified, which is very on brand for string theorists, frankly. M-theory required something even stranger, an 11th dimension. Not 10, 11. The 5 string theories were different 10-dimensional slices through a single 11-dimensional reality. And this 11th dimension wasn't just curled up like the others. It had different properties, allowing for membranes, multi-dimensional objects, not just one-dimensional strings, to exist. So now we have 11 dimensions, most of them invisible, populated by vibrating strings and membranes, with the entire universe being one possible configuration among many. It's magnificently ambitious and simultaneously impossible to visualize. How do you picture 11 dimensions? You can't. Our brains evolved in 3 dimensions. We're simply not equipped for this. But mathematically, it works. The equations are consistent. The framework is elegant. It unifies the 5 string theories into a single picture. And it still includes gravity naturally, still avoids the infinities that plague other quantum gravity approaches. On paper, It's beautiful. There's just one tiny problem. We have absolutely no idea if any of it corresponds to reality. We can't test it. We can't see the extra dimensions. We can't detect the strings. We can't produce supersymmetric particles. M-theory might be a perfect mathematical description of our universe, or it might be an elaborate fantasy with no connection to the actual world. And that's the central tension in string theory. It's mathematically beautiful, conceptually unified, and potentially the deepest truth about reality we've ever uncovered. Or it's the most elaborate mathematical game ever played, with no relevance to physics whatsoever. Physicists have been arguing about which interpretation is correct for decades now, and we're still no closer to settling it. Have you ever built something intricate and beautiful, maybe a model, a piece of art, an elaborate plan, only to step back and wonder if it actually serves any purpose? That's the question hovering over string theory. It's magnificent, but is it real? Now you think having one unified theory would simplify things, but string theory had one more surprise waiting, and it's a doozy. It turns out there isn't just one way to configure those extra dimensions. There are many ways, possibly 10 to the power of 500 different ways. That number is so large it's effectively meaningless. To put it in perspective, there are only about 10 to the power of 80 atoms in the observable universe. The number of possible string theory configurations is unimaginably larger than that. Physicists call this enormous collection of possible universes the landscape of string theory. Each point in the landscape represents a different way the extra dimensions could be curled up, leading to a different set of physical laws, different particles, different force strengths, different constants of nature. Some of these universes would have life, most wouldn't. Some might have chemistry, others might not have stable atoms. Each one is a possible universe that string theory allows. Now here's the question that's been tormenting string theorists since this was discovered in the early 2000s. Which one is our universe? Out of 10 to the power of 500 possibilities, which specific configuration describes the reality we inhabit? For a theory of everything, this is rather problematic. The whole point was to have a theory that uniquely predicted our universe's properties, but instead, string theory says almost anything is possible, somewhere in the landscape. It's a bit like asking for directions and being told, you could be absolutely anywhere on Earth. Technically true, but not terribly helpful. Some string theorists argue this is actually fine. They point to the anthropic principle, the idea that we observe the universe we do because it's the kind of universe that allows observers to exist. If different regions of space have different configurations, different bubbles of space-time with different laws of physics, then obviously we find ourselves in one of the rare configurations that permits life. All those other 10 to the power of 500 universes exist too, we just can't see them because we're here and not there. This connects to the idea of the multiverse. Not just multiple universes in the sense of string theory's landscape, but actually existing regions of space with different physical laws, potentially created during cosmic inflation in the early universe. Our universe is one bubble in an enormous cosmic foam, each bubble with its own properties. It's philosophically troubling for many physicists. Science is supposed to predict things, to narrow down possibilities. But if string theory says almost anything can happen somewhere in the multiverse, what exactly has it predicted? How do you test a theory that's compatible with almost any observation? Critics call this unfalsifiable. If you can't prove it wrong, Is it even science? Karl Popper argued that for a theory to be scientific, it must make predictions that could potentially be proven false. If string theory predicts that our universe is one of 10 to the power of 500 possibilities and we can't test the others, have we left the realm of science and entered mathematical philosophy? String theorists push back against this. They argue that the framework is falsifiable in principle. If we built a powerful enough particle accelerator, we could potentially detect supersymmetric particles or other signatures of string theory. The problem is practical, not philosophical. We simply don't have the technology yet. Others suggest more indirect tests. Perhaps string theory makes predictions about cosmology, about patterns in the cosmic microwave background or the nature of dark matter. Maybe careful observations of the early universe could reveal evidence for or against the theory. But so far, nothing. Particle accelerators have found no supersymmetry. Cosmic observations have found no clear signatures. String theory remains, after 40 years of intensive development, empirically unconfirmed. There's also the small matter of actually calculating things. String theory's mathematics is phenomenally complicated. Physicists can work out certain properties relatively easily, but extracting specific predictions for measurable quantities is extraordinarily difficult. Often it's simply beyond current mathematical techniques. This means that even if string theory is correct, we might not be able to use it to predict what we'd actually observe in experiments. It's a theory that describes everything but can calculate almost nothing, at least not yet. Like having a map of an entire country but drawn in a language you can't read. So where does this leave us? We have a mathematically consistent framework that unifies all forces, includes gravity, and requires no arbitrary adjustments. But it exists in 10 or 11 dimensions we can't see, predicts particles we haven't found, and allows for vastly more possible universes than we can ever explore. It's either profound truth or elaborate fiction, and after decades of work we still can't tell which. The thing is, physicists are clever. They're deeply aware of these problems. Entire conferences are devoted to discussing how to test string theory, how to extract predictions, how to connect the mathematical framework to observable reality. Thousands of brilliant minds are working on this, not out of stubbornness, but because the mathematical beauty and internal consistency of the theory suggest it's pointing towards something real. Or maybe they're all caught up in an intellectual edifice that's magnificent but fundamentally disconnected from the actual universe. Honestly, we don't know, and that uncertainty is both frustrating and thrilling depending on your perspective. Right, let's address the elephant in the room, or rather the absence of the elephant since we can't actually see it. String theory has critics, lots of them, and some of these critics are very, very smart physicists who think the whole enterprise is a spectacular waste of time and talent. The most prominent critic is probably Lee Smolin, a physicist who wrote a book called The Trouble with Physics in 2006 outlining his concerns. He argues that string theory has consumed vast amounts of intellectual resources, thousands of physicists, decades of work, countless papers and conferences, but has produced essentially no testable predictions and no connection to experimental reality. Smolin suggests this has become a sociological problem as much as a scientific one. Universities hire string theorists because string theory is prestigious. Students study strings because that's where the jobs are. Conferences focus on string theory because that's where the excitement is. It's become a self-reinforcing cycle where the dominance of string theory isn't due to empirical success, but to academic momentum. Another critic, Peter Voigt, wrote, "Not even wrong," a phrase borrowed from physicist Wolfgang Pauli, who allegedly said it about theories so poorly formed they couldn't even be proven incorrect. Voigt argues that string theory, with its vast landscape of possibilities and lack of concrete predictions, has become unfalsifiable and therefore unscientific. Now, string theorists obviously disagree. They point out that scientific progress isn't always linear. Quantum mechanics took decades to develop and faced plenty of skepticism along the way. General relativity made predictions that couldn't be tested for years. Judging a theory before the necessary technology exists to test it seems premature. They also argue that string theory has produced significant insights even if it hasn't been experimentally confirmed. The mathematics developed for string theory has found applications in other areas of physics, including fluid dynamics, condensed matter physics, and even pure mathematics. The ADS/CFT correspondence, a connection between gravity theories and quantum field theories, discovered through string theory research, is used by physicists working on problems entirely unrelated to strings. But the critics counter that this isn't the same as being correct about reality. A theory can be mathematically interesting and physically wrong. The question isn't whether string theory is beautiful, or whether it's inspired useful mathematics elsewhere. The question is, does it describe our universe? There's also a more subtle concern. Physics has always been guided by experiments. Theory and experiment work together, each informing the other. Theorists propose ideas, experimentalists test them, and the results guide the next round of theories. It's a dialogue, a back and forth that's driven physics forward for centuries. But string theory has developed largely in the absence of experimental feedback. For 40 years, it's been primarily a theoretical enterprise, driven by mathematical consistency and aesthetic appeal, rather than empirical data. This worries some physicists. Are we doing physics or are we doing applied mathematics? Without nature telling us if we're on the right track, how do we know we're not wandering down an intellectual dead end? There's a famous quote variously attributed that goes something like, "In theory, there's no difference between theory and practice. In practice, there is. String theory is magnificent in theory, but in practice it's had 0 confirmed predictions about the physical world." Now, to be fair, testing fundamental physics is getting progressively harder. The energies required to probe the Planck scale, where string theory's effects would be noticeable, are absurdly beyond anything we can achieve. We'd need a particle accelerator the size of the solar system. That's not happening anytime soon, or possibly ever. This raises an uncomfortable question. What if the ultimate nature of reality exists at scales we can never directly probe? What if the final theory of everything is experimentally inaccessible? Do we just give up, or do we follow the mathematics wherever it leads, hoping it's pointing toward truth even if we can't verify it? Different physicists answer this differently. Some think mathematical beauty and internal consistency are reliable guides when experiments aren't available. Others think physics without experimental verification isn't physics at all. And so the debate continues. String theorists keep working, convinced they're on the right track, that the mathematical elegance and unifying power of the theory are too compelling to ignore. Critics keep objecting, arguing that beauty isn't truth and that physics needs to reconnect with observable reality. Meanwhile, the universe keeps its secrets. Black holes don't reveal their inner workings. The Big Bang's earliest moments remain hidden. Quantum gravity's correct description eludes us. And string theory sits in this peculiar space, simultaneously the most developed candidate for a theory of everything and entirely unproven. It's genuinely one of the most interesting intellectual situations in modern science. Not because we know the answer, but because we don't. Because smart people disagree fundamentally about whether this entire edifice is profound or pointless. Because after 40 years, we're still not sure. Have you ever committed deeply to something, invested time and energy and belief, only to wonder if you've made a mistake? Whether you should have chosen differently, taken another path? That uncertainty, that vulnerability to being wrong despite your best efforts, that's rather human, isn't it? Even physicists feel it. Drift off pondering whether mathematical beauty is a reliable guide to truth or just a seductive illusion. Right, let's venture into the really speculative territory now. We've talked about what string theory is, how it developed, and why it's controversial. Now let's talk about what it might mean for some truly mind-bending ideas: parallel universes, the nature of time, and whether time travel is possible. First, the multiverse. We mentioned the landscape earlier, those 10 to the power of 500 possible configurations. But string theory combined with cosmic inflation suggests something even stranger. All of those configurations might actually exist, not just as mathematical possibilities, but as real physical regions of space. During inflation, the rapid expansion in the early universe, different regions of space could have inflated with different configurations of the extra dimensions. Each region would have its own laws of physics, its own particles and forces. These regions would be causally disconnected from each other, separated by such vast distances that light from one could never reach another. They're effectively separate universes, all existing within the same overarching reality. This means you're not just in one universe among many possible universes, you're in one universe among many actual universes. Somewhere, in a region of space so far away you'll never see it, there might be a universe where electrons are heavier, or where gravity is weaker, or where the strong nuclear force doesn't exist and atoms can't form. An infinity of variations, all real, all out there. It's philosophically dizzying. The universe, or rather the multiverse, isn't just bigger than we thought. It's fundamentally different. Reality isn't one thing with one set of rules. It's a vast tapestry of different realities, each with its own character. Now, what about time travel? This is where things get particularly interesting. String theory allows for configurations of space-time that include closed time-like curves, paths through space-time that loop back on themselves, allowing travel to your own past. In classical general relativity, these closed time-like curves create paradoxes. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you're never born. But if you're never born, you can't travel back in time to prevent their meeting. It's a logical contradiction. String theory, with its multiple possible universes, offers an elegant solution. When you travel back in time, you don't travel back in your own timeline. You travel to a parallel timeline, a different branch of reality. In this timeline, you can prevent your grandfather from meeting your grandmother. But it doesn't affect your timeline, where you were born normally. You've simply created or travelled to a different history. This idea connects to the many worlds interpretation of quantum mechanics, which suggests that every quantum measurement splits reality into multiple branches, each representing a different outcome. Travel to the past and you're moving between these branches, not creating paradoxes within a single timeline. Now, I should stress, this is highly speculative. String theory allows for these possibilities mathematically, but whether they exist in reality is entirely unknown. We have no evidence of closed time-like curves, no observation of parallel timelines, no confirmed detection of any aspect of string theory at all. This is speculation built on speculation, mathematical possibility rather than established fact. But it's fascinating speculation. The idea that every possible history might exist somewhere, that time travel might be possible without paradoxes, that reality is vastly more complex and strange than everyday experience suggests. It's the kind of idea that captures imagination precisely because it's so far beyond what we can currently verify. String theory also suggests that information is never truly lost, even in black holes. This resolves the black hole information paradox, another problem in quantum gravity. If information is preserved, then the universe's quantum state is always well defined, and time evolution is consistent. The mathematics of string theory ensures this, providing solutions that other approaches struggle with. Looking forward, what's the future of string theory itself? Well, that depends on whom you ask. Optimists believe we're still in the early stages, that future mathematics and future experiments will vindicate the framework and reveal its connection to reality. They point to ongoing work in understanding M-theory, developing computational techniques, and searching for novel predictions. Pessimists think string theory has reached its limits without experimental guidance, that it's become an intellectual exercise disconnected from physics. They advocate for exploring alternative approaches to quantum gravity, like loop quantum gravity or causal set theory, hoping a fresh perspective might break the impasse. And many physicists are somewhere in the middle, continuing to work on strings while remaining open to other possibilities, aware that nature might surprise us entirely with a solution nobody's considered yet. The honest answer is, we don't know what happens next. Maybe someone makes a breakthrough tomorrow, finding a testable prediction or a clear connection to observations. Maybe experiments discover supersymmetry or extra dimensions, confirming aspects of string theory. Maybe we realize the whole framework is wrong and pivot to something else. Or maybe we spend another 40 years in this uncertain state, making mathematical progress but lacking empirical confirmation. What I find remarkable is the sheer ambition of it all. String theory attempts to explain everything, from the smallest particles to the largest structures, from the Big Bang to black holes, from quantum mechanics to gravity. It's humanity reaching for the ultimate understanding, trying to grasp the deepest workings of reality itself. We might be wrong, we might be chasing shadows, but we're asking the biggest questions we can conceive, and that's worth something, isn't it? Even if string theory turns out to be incorrect, the effort to understand reality at its most fundamental level is a deeply human endeavor. We're pattern-seeking creatures, storytelling animals, compelled to seek explanations for the world around us. And sometimes the journey matters as much as the destination. String theory has taught us to think bigger, to question our assumptions about dimensions and reality, to follow mathematics into strange territories. Whether it's ultimately right or wrong, it's expanded our conception of what's possible. Think about the fact that you exist at all. You're a collection of particles arranged in a configuration that can contemplate the universe's deepest workings. Those particles might be vibrating strings, or they might be something else entirely. But either way, you're here, conscious, aware, wondering about reality's true nature. That's rather spectacular, regardless of whether string theory turns out to be correct. So where does that leave us at the end of this journey? String theory remains unproven, controversial, and absolutely fascinating. It might be the greatest intellectual achievement in physics, or it might be a magnificent detour. We're living through the story, unable to see its ending yet. And honestly, that's perfectly all right. Science isn't always about having answers. Sometimes it's about asking better questions, exploring possibilities, pushing the boundaries of what we understand. String theory has done that, and will continue to do so, whether it's ultimately vindicated or not. Sleep peacefully knowing that somewhere physicists are still working through the mathematics, still searching for that crucial insight, still hoping to understand reality's deepest truths. And perhaps, in some other timeline allowed by string theory's equations, they've already figured it out. And that brings us to the end of our journey through string theory's wonderfully weird world. From the desperation that led physicists to propose vibrating strings in the first place, through the explosive excitement of the 1980s revolution, the humbling discovery of the vast landscape, the fierce controversies about whether it's science or philosophy, and finally, to those tantalizing speculations about parallel universes and time travel. It's been quite the expedition, hasn't it? We've explored 10 or 11 dimensions, most of them invisible. We've contemplated 10 to the power of 500 possible universes. We've wandered through one of the most ambitious intellectual projects in human history, a framework that attempts to explain literally everything, but remains frustratingly unproven. If you're still awake at this point, I'm genuinely impressed with your stamina. I hope your mind is pleasantly full of vibrating strings and hidden dimensions, and the peculiar beauty of mathematics that might or might not describe reality. These are good things to drift off thinking about, I reckon. Better than worrying about tomorrow's meetings or that embarrassing thing you said 3 years ago that nobody else remembers. The story of string theory is really a story about human ambition and uncertainty, about brilliant minds reaching for ultimate understanding, following mathematics wherever it leads, even when it leads to places we can't directly observe, about the tension between beauty and truth, between theoretical elegance and experimental verification. It's also a reminder that science isn't finished. We haven't figured everything out. There are profound mysteries remaining at the heart of physics, and we're still grappling with them. That's thrilling, really. We live in a time when the universe still has secrets to reveal. Thank you for spending this time here, for letting me guide you through one of physics' most controversial and captivating ideas. I know I've been whittering on, but I hope it's helped you relax, that it's given your mind something intriguing to contemplate as you drift towards sleep. I'd be genuinely curious to know what you think. Does string theory sound plausible to you, or like an elaborate mathematical fantasy? Does the idea of hidden dimensions and vibrating strings resonate with you, or does it seem too strange to be real? Drop a comment and share your thoughts. And if you're a physicist who thinks I've oversimplified or gotten something wrong, please let me know gently. I'm doing my best here. If you've enjoyed this gentle exploration of theoretical physics at its most ambitious and uncertain, a like would be enormously helpful. And if you'd like more of these peaceful journeys through science's big questions, do consider subscribing. It helps this little channel reach other wonderfully curious, delightfully sleepy people who enjoy pondering the universe's mysteries while trying to drift off. Also, if you would like me to do a topic you haven't heard elsewhere, drop a comment below and I will look into that for you. For those of you who've been here before, thank you. You're building this small community of people who find comfort in contemplating reality's deepest puzzles. That means more than I can adequately express. I'll leave you now with some gentle sounds to help you complete your journey into sleep. And if you've already drifted off, well, it means you didn't have to hear me wittering on. I hope you have pleasant dreams of cosmic symphonies and parallel timelines, of hidden dimensions and elegant mathematics, of a universe far stranger and more wonderful than everyday experience suggests. Until next time, sleep well, and remember, whether you're a point particle or a vibrating string in 11 dimensions, you're here, you're conscious, and you're part of this magnificent, mysterious universe. Good night and sweet dreams.